Hello students, in this video I am going to discuss about the chapter electromagnetic induction which is present or magnetism which is present in ICSE class 10. It is one of the most conceptual portion and majorly divided into two parts I will say. One is the force experienced by a conductor, current carrying conductor in a magnetic field, and the second part involves motional EMF or we can say induced EMF. So let us discuss one by one. First is what is force experienced by a conductor in a magnetic field. So let us consider a conductor. This is a conductor which is carrying some current I, and this conductor is placed in a magnetic field, external magnetic field. For just convenience, I am drawing here crossed magnetic field. As you can see, this is a cross magnetic field. So when this conductor is placed in a cross magnetic field or magnetic field, this conductor will experience a force. Now, of course, there is a magnetic field due to this conductor which is carrying current. This will also exert a magnetic field here. So, because we have already put this conductor in an external magnetic field, so the general formula for the force experienced by the conductor carrying current is F equal to ILB, where I is the current of the conductor, L is the length of the wire, and B is the magnetic field. Now, the very common misconception is if you increase the current, of course, the magnetic field will increase. If you increase the length, then if you increase the current, then force will increase. If you increase the length, then force will also increase. The force experienced by the conductor will increase. And if there is increase in the magnetic field, then also the force experienced by the conductor will increase. Now, interesting thing about this concept is this particular wire can never experience its own magnetic field. So since it cannot experience its own magnetic field, this means it cannot experience force due to its own magnetic field. That is why we have kept this wire in an external magnetic field. So once we increase the current in this wire, there will be a magnetic field which will be exerting some force on the source, which is not discussed here. Of course, there is some source due to which there is an external magnetic field. So this magnetic field will exert a force, and in return the external magnetic field will exert a force on this wire, and that force will be experienced by the wire. For example, I cannot or we cannot experience gravitational field due to our own mass, and of course we cannot experience the force, gravitational force due to our own mass. So in a similar manner, if this particular conductor is carrying current and it is of course having some magnetic field and it will exert a force as well, but this particular wire will not be able to experience it unless there is an external magnetic field. So more is the current, more is the magnetic field exerted, more is the magnetic field and more is the force exerted by this current carrying wire on the external magnetic field, and in return external magnetic field will exert a force which will be experienced by this wire. So this is the basic understanding. When a conductor carrying current is placed in a magnetic field, the force experienced is ILB. So it is directly proportional to the current flowing through the conductor, directly proportional to length of the conductor, and of course directly proportional to the external magnetic field as well. Okay, we will consider that the external magnetic field, this external magnetic field is always very bigger than compared to the magnetic field of the rod. Okay, so you can pass any amount of current, but the magnetic field which will be created by this current carrying wire will be far less compared to the magnetic field of the source, which we have not discussed anywhere in any book, even in your books that you read in class 10. So this is a very basic understanding of how force is experienced by a conductor in a magnetic field. So here we have to understand that this wire is acting like a test conductor which can experience a magnetic force when placed in an external magnetic field. Now students, let us move to another very intriguing topic, which is electromagnetic induction, or how the EMF is induced in a conductor. It's a very simple topic otherwise. Remember, if there is some relative motion between the conductor and the coil, suppose this is a conductor and of course there is a coil as well. So if there is a relative motion between the conductor and the coil, then only it is possible that EMF will be induced. Why? Because there will be change in flux. If there is no relative motion between the conductor and the coil, then EMF will not be induced. We have to understand that. So that is why we say that this is also called induced, this is also called motional EMF. So the EMF which is induced due to the motion is called motional EMF. Suppose we have a conductor rest with velocity v equal to 0 and there is a coil which is moving with some velocity v towards the conductor. So there is a relative motion. So it is also possible that the coil is at rest and the conductor is moving, or the conductor is at rest, the coil is at rest, conductor moving, and conductor is at rest and coil moving. Both type of motion is possible, but there must be some relative motion. Now what will happen if both the conductor and the coil both are moving in the same direction? Suppose both are moving in the same direction. If the velocity of the conductor and the coil both are same, remember this is the concept here. If the conductor and the coil both have the same velocity, in that case there is no induced EMF because there will be no flux change. But in case even if there is some slight variation of velocity between the two, at some point of time flux will be induced and of course EMF will be induced. There will be change in flux and EMF will be induced due to difference in the velocity. So always remember, unless there is a relative motion, EMF induced is induction of EMF is not possible. So there must be relative motion. That's why we say if there is a relative motion between the conductor and the coil and EMF is induced, which is called induced EMF. So this is a basic understanding, and we already know how to find the direction of the induced EMF by using Lenz law. According to Lenz law, the direction of the induced EMF is such that it opposes the cause which is producing it. Now what is the cause? Cause, remember, the motion. It will oppose the motion. For example, if I am bringing the coil towards the conductor, so in that case, if this particular coil is moving towards the conductor, this coil will be developing opposite pole so that it can push it away. So if the coil is moving away, then the polarity developed will be such that it will pull it towards the conductor. So that is Lenz law. Lenz law gives us the direction of the induced EMF. And it states that the direction of the induced EMF is such that it opposes the cause which is producing it. जिस कारण से ये relative motion है, उस कारण को ही वो oppose करेगा. Means it will oppose the motion. So that is Lenz law. And remember, Lenz law is also connected with law of conservation of energy. How? Because it is not possible that the conductor is moving by itself. You apply some force, you give some force. Now when you are applying some force and there is some motion, work is done. So this work done is basically mechanical energy, and this mechanical energy is getting converted into electrical energy. So it is following law of conservation of energy, according to which whatever energy you are giving in, same amount of work will be done. Considering there are no energy losses, so we can consider that Lenz law is connected with law of conservation of energy, as we apply some mechanical energy here and that mechanical energy is getting converted into electrical energy when EMF is induced. When EMF is induced, of course you will find that current is starting to flow. So that is due to law of conservation of energy. So this is a small video. In this video we will end this particular topic of electromagnetism. The topics that we discussed here was mainly two topics: force experienced by a conductor in a magnetic field and what exactly is electromagnetic induction. Another point before ending is, remember, the rate of change of flux d phi by dt is proportional to EMF. Means EMF directly depends upon flux, how flux is changing, and you know that flux is nothing but number of lines of or number of field lines passing through any given area. किसी area के ऊपर से कितने field lines pass कर पा रहे हैं, that is called flux. So this change in flux is directly proportional to EMF. Means जितना ज़्यादा flux change होगा, उतना EMF induce होगा. Remember, in higher classes you will learn though that this particular flux or field lines that is passing through any given plane can make some angle with the plane. So in that case, it is actually area becomes a vector quantity. So here this particular law is called Faraday's law of electromagnetic induction. It states that the EMF is directly proportional to rate of change of flux, and the induced EMF will exist till there is a change in flux. जब तक फ्लक्स चेंज होगा, EMF इंड्यूस होता रहेगा. Always remember, suppose this is a magnetic field. Let us understand this. Suppose I draw a crossed magnetic field here. This is a region where there is a crossed magnetic field like this. Okay, and I am trying to bring here a particular coil which is carrying some current. Okay, is carrying some current, and when I move this coil inside and outside, there is a change in flux, because the area inside and area outside will be changing for this particular coil, rectangular coil. So in that case, flux will be induced. So because here area is changing, that's why the number of field lines passing through this given area also changes. That's why flux will be induced. So this is what I mean by Faraday's law of electromagnetic induction. EMF is directly proportional to rate of change of flux. So how the flux is changing, EMF will be induced according to that. So thank you students for watching this video for ICSE Physics 2026. Thank you.